Yes.
Okay, good afternoon, everyone. I am Anjan BK. I welcome you all to day 16 program for our online gate coaching. For the first session, will be on steel structure by Professor Rajeeth T J, and he is working here as an assistant professor in the Department of Civil Engineering, Vidyavardhaka Engineering College, and he is having a total experience of 6 years in teaching, and he has completed his engineering as well as master CE Mysuru, and he is going to handle this today's first session on steel structure. So without wasting further time, I request and I welcome Professor Rajeeth T J to take over the session. Thank you.
Thank you, Professor Anjan. So I welcome all the GATE aspirants to the 16-day session 1 on subject steel structure. So in the last session on 12th of this month, we have covered so many topics here. In that we have covered working stress method limited concepts, and we have covered simple and eccentric connections with regard to the bolted connection. So yet to complete the welded connection. So remaining topic I will cover today, the remaining portions. So let me start with the example problem on welded connection. So this was a 2 marks question. So I will read the question. So two plates are connected by the fillet welds of size 10 millimeter. So two plates having a size of 10 millimeter here. Subject to tension as shown in the figure. The thickness of the plate is 12, sorry. So 10 mm is the fillet size. The yield stress and ultimate strength of the steel is given directly here. So 250 MPa and 410 MPa. 250 is the yield stress of the material. 410 is the ultimate strength of the material. The welding is done at workshop. So here they given the information about where the welding taken place. So welding was done at a workshop. Therefore, the gamma MW partial safety factor for a shop fabricated weld is 1.25. The information is given here. So this was the figure they provided. So width of the plate, bottom plate is 150 millimeter, top plate is 10 mm. Whereas the size they used both the sides, fillet weld of size 10 mm size fillet weld, S equal to 10 mm. So okay, here if you observe, force is applying on the the top plate of width 100 mm width. So force is P. So what they are asking here, as per the limit state method of design, IS 182 to the nearest highest multiple of 5 mm. The answer you should keep in the nearest highest multiple of 5 millimeter of each weld to transmit force equal to 270 kilonewton. Okay, 270 P is a 270 kilonewton load, for which we need to design the weld. So here what we can do is you can take directly P equal to 270 kilonewton. Okay. So otherwise, if they're not given any information about the load, that is P value. So what we can apply here is we can apply the maximum load that can carried by the plate. The maximum load carried by the solid plate is the formula. So load equal to AgFy by gamma m naught, that is P. So instead of that, you can take 270. If this information is not given, if they given like for the full strength of the plate, you can provide the weld like that. Then you can take P equal to AgFy by gamma m naught. Here we have calculated that value. Ag is gross area of the plate 100 into 12 millimeter. The top plate into 250 is the yield strength of the material Fy. Gamma m naught is the yielding partial safety factor 1.10. We are getting 272 kilonewton. So since we are getting the total load as P as 270 kilonewton, but this total force, that is 272, I am calculated here by taking full length area. Otherwise, you can take 270 also. You will going to get the same answer. So here this 270 or 272 will be shared by two welds. So this weld on one side and another one is on this weld. So I need to take half of the load. I can analyze the one side of the weld. Same size will be applicable for this. So therefore, that for that I have taken what? P by 2, that is 272 by 2, 136 kilonewton. If you take 270, you're going to get 135 kilonewton. Then minimum size of the weld I should calculate here. So minimum size of the weld here. So in the multiple of 5 millimeter. What we have the formula? Strength of the weld equal to load carrying capacity of the weld. So strength of the weld is, I discussed yesterday class, strength equal to, strength is nothing but the load carrying capacity of the weld, that is equal to area in the area of the weld into area of the weld into the stress in the weld. So here area of the weld is this much. We are discussed in the last session. The same thing, area equal to length into throat thickness into stress Fu root 3 gamma mw is the stress in the material. This is equal to load carrying capacity. Since we know the load, I have written on the RHS side. So that is 136.36 10 power 3 Newton. Here I have written in terms of Newton. Why? Because Fu. So on the other side, Fu I need to substitute in terms of Newton, 410 Newton per millimeter square. Therefore, all units are in the millimeter, the length units, the load units in Newton. So this is what the area of the weld. So the LW into throat thickness. Throat thickness is what? Your formula is throat thickness for is K into S. Okay, where K for for alpha 60 to 90 degree. So K is what? 0.7. So you should remember that value. For almost all the problems, K would be 0.7 only. So size of the weld is given is 10 millimeter. So stress in the ultimate stress in the material 410. So 1.25 here they have taken 1.2. Actually, this you should take 1.25 the gamma mw. So this is equal to load carrying capacity. You're getting here 1 or 2 millimeter. If you rounded it to nearest 5 millimeter multiple, you're getting 1 or 5 millimeter is the length of the weld I should give to the what? To each weld. To the each weld to transport a force equal to 270. This is what I have calculated for this. Same thing it should be for this. Total length of the weld for entire problem is, entire load is what? 210 millimeter, 105 plus 105. Whereas for each weld, this is answer is 105 millimeter. This is your answer. So how to calculate the length of the weld required for the given problem. Okay. So then we move on to one more problem here. So we'll read the problem. So two plates of 8 millimeter thickness, each are connected by a fillet weld of 6 mm size. So size of the weld is 6 mm here, as shown in figure. So this is what the plate they have connected 100 mm plate, and another one is what the width of the plate here is 50 mm plate. The total length of the weld here provided is, if you observe the figure, 100 millimeter at the top, 100 millimeter at bottom, total 200. Plus on the other side also they have provided 50 millimeter. Therefore, total weld is provided is 2 times of 200 plus 50, 250 millimeter. Total length is weld is provided. So around 50 mm thick plate they have provided the weld. Okay, size of the weld here is 6 millimeter. So force is acting here, and either say there is a tension member. The permissible stresses in the plate and the welds are, so here they given permissible stresses directly. Therefore, this may come under working stress method. No need to worry. If they given permissible stress directly, you can take the stress as a stress for our calculation. Okay, you can apply working stress. Otherwise, if they are not given any information, if they given partial safety factor and ultimate stress information, then you can apply limit state method. Okay, in your syllabus we have both working stress limit state concepts. So the permissible stress in the plates is 150 millimeter for plate, and the yield stress for weld is 110 millimeter. So plate is having more permissible stress compared to weld. So assuming length of the weld as shown in figure, so length is given here. So you should calculate the permissible load P in kilonewton. The permissible load P in kilonewton I should calculate for the given condition, where condition here is they used 6 mm size fillet weld, and they used 3 sides welding here of total length 100 plus 100 plus 50. So first I should check. So what is the permissible load? Nothing but the least load that we can apply on this chart. The least load I should calculate with respect to the plate once. So I should assume that the plate will fail like that. Then I should calculate the the strength of the plate. Only the plate 50 mm plate I should check for that. Then I should check for the strength of the weld. So whichever is least, that is the load what we can apply on this chart. So first I will go for strength of the weld. So for strength of the weld, I have told that load strength is nothing but load carrying capacity of the weld. Load carrying capacity equal to area into stress or stress into area. So what is the permissible stress in the weld is 110. So therefore your FEB will equal 110. So when you come to the area, so length into throat thickness, So what is the total length of the weld here? 100 plus 100 plus 50, total 250 here. We written LW, L effective, into K into S. K is 0.7. I told for all the problems almost K equal to 0.7 if not specified. Since our the fluids will meet at exactly 90 degree. So 0.7 into size of the weld is 6 millimeter here. Fillet size is given as 6 mm. So therefore, the load carrying capacity for welding here is 115. So what does it mean? So if you apply more than this, there is fraction of load, the weld will fail. So in the similar way, this is what the capacity of the weld. In the similar way, we go for capacity of the plate, that is stress into area. So stress into area is, we should take what the smaller plate 15 to 8 mm, so on which we are applied the weld. So into permissive stress in the plate, that is here given is 150 millimeter. If you apply, we are getting 60 kilonewton. So therefore, out of 2, so this 115 and 60 which is least, so 60 is the least. That is, if you apply 60 kilonewton, so if you apply more than a fraction of load more than 60 kilonewton, the joint will fail here. So the plate will fail. Therefore, this is the permissible load. So answer for this is 60 kilonewton. This is a numerical answer type question. There is no options for this, multiple choice, and also there is no negative marking for this. I should calculate and type your answer. That is your answer. So if you move on to the next problem. So one more problem on welding connections. So in a fillet weld, the direct shear stress and bending tensile stress. So here they given the stresses here. The shear stress is 50 MPa, bending stress is 150 MPa. As per IS 810-2007, the equivalent stress in up to 2 decimal places we should calculate. So this one we should calculate according to the code. We discussed this one in the last session. The formula for equivalent stress when the bending stress, shear stress is acting on the welded joint, this is the formula we should calculate. But anyhow, this value must be less than this, your permissible strength of the weld, that is strength of the weld. So therefore, so according to the class 10.5.10.11 of IS 18-2007, this is the formula. So effective stress equal to what? Or equivalent stress equal to square root of FA square plus 3Q square, where FA is what? The bending tensile stress. Q is what? Your direct shear stress. If you substitute the corresponding values here, 150 square plus 3 into 50 square, you're going to get 173.27 MPa, 21 MPa. Then you compare this value with your strength of the weld. That is, according to the code, the strength of the weld is Fu root 3 gamma m naught at any stage. So the strength here is what? The here if you substitute here Fu, so 400 by root 3 gamma 1.25, you're getting 184. Therefore, your answer is out of these two, whichever is least, that is your what equivalent stress in the joint. Therefore, your answer is 173.21 MPa. So this is also one of the previous year gate problem. So we'll move on to next question. So we'll move on to now the design aspects of tension members. So the normally in the truss or in a building, the members which are separated to two equal and opposite forces, that member will be separated to what? A tension. If I apply for tension forces, so where we can calculate the various strength in the tensile member or the tensile joint. The members of tensile forces. So first, according to the code, we should calculate what the gross strength yielding or yielding of the cross section TDG. You should remember some of this formula. It may the problems here. TDG AGFI by gamma m naught. So next strength is the strength due to rupture of the cross section 0.9 ANFU by gamma m1. Okay. So for threaded rods, this value will vary 0.9 ANFU by gamma m1. For single angle, it will vary like this 0.9 ANC FU by gamma m1 plus beta AGO FI gamma m naught. Okay. So for black shear strength, so this is the formula AGFI by root 3 gamma m naught plus 0.9 ATN FU by gamma m1. This one formula for TDB. So another one is 0.9 AVN FU by root 3 gamma m1 plus ATG FI by gamma m naught. Okay. This is what the things you should remember, some of the formula. So till now we have used this formula, TDG formula. For other informations like black shear and other things, so they will give the information about the partiality factors. Otherwise, we should know this partiality factor for all the conditions. So lug angle is used to, in the tension members to reduce the connection length. So some of the aspects they are given in 10.12. Should look into it. So they haven't asked till this year. So they will going to frequently ask the things related to lug angle in IES examination. So you can refer class 10.12 for more information. So next, go for one review question on tension member. A steel flat of a rectangular section of size 17 to 6 millimeter, 17 to 6 millimeter is connected to the gusset plate by 3 bolts. 3 bolts they are connected. Okay. Each bolt having a shear capacity of 15 kilonewton. That is shear capacity of the bolt capacity of the bolt is 15 kilonewton, the single capacity. So this having a hole diameter equal to 11.5 millimeter. If the allowable stress in the tensile plate is, that is plate in the plate, the allowable stress is 150 MPa. The maximum tension that can apply to the flat is. So that is, I should go for, they will here in this problem, they're given what some, plate is connected to gusset plate, the information. They're connected using 3 bolts of diameter is not given here. They're given directly the bolt hole clearance, that is 11.5 millimeter. Okay, they're given in this pattern. So with respect to the plate, so plate is having what 70 meter width and thickness is 6 mm. With respect to the plate, they're given the edge distance and pitches. Okay, so and edge distance and gauge distance, all the distances are provided here in the drawing. So what we need to do here is, so what is the maximum tension we can apply on the flat? Here is the option 42.3, 52, 59 and 63 are the options. So what we can calculate here is, first I should calculate what the strength of the net tensile strength at different sections. That is, I should take one section on and this port. So first port from your left hand side. So then, so if you go for, so another one strength on different section. So where if you calculate the, you should take the section along this port, that is called as 1 1. So another section I have chosen here is 2 2. Okay. Then you calculate along 1 1. The net area will be out of 70. If you're considering now, if you're considering the first case now, the 70, first board. Okay. So A net will be equal to us 70 minus 11.5. 11 is what? The area of the bolt hole provided here. Okay. So in that, if you deduct what the diameter of the bolt hole, 11.5 out of 70 into multiply by 6, you're going to get the net area. So for this net area, if you multiply the yield stress, you're going to get the lower carrying capacity at this junction. So that junction area is carrying what 52.65 kilonewton. In the similar way, we should calculate net area along 2 2. So then in 70 mm, you should deduct how many bolt hole? You should deduct here 2 bolts hole here. So each bolt hole consisting of the diameter is 11.5 millimeter. So therefore 70 minus 2 into 11.5. This is what your actual length after deducting the bolt hole here. Out of 70 you will going to have. So into 6 mm thickness, you will going to have 282 millimeter square area. So you multiply the area with stress, you're going to get the load that is equal to 42.3. So out of this, which is whichever is least, that is your answer here. So out of 52.65 at section 1.1, section 2 to 42.3. So section 2 is critical section. Why? Because in the grass area we are deducted 2 diameter of the bolt holes. So therefore here we have less area. So since load is directly proportional to the area, if you have less area, definitely going to get lesser load. So the load has to be calculated here. Why? Because they are given in terms of the loads here, not in terms of section. If it is a section, then you can tell directly here, this was the critical section. Wherever you have more number of bolts, that is what our critical section for tension. Since we're going to have what the lesser area there. Okay, this was the problem. Then if you move on to the next slide, that is slenderness ratio. This is one of the important parameter we're going to use frequently for tension member, compression member design. In some of the cases, check in tension also. So this is given in table number 3. So this very, very important table. So table number 3, you should remember this. So I will read the values here. The maximum slenderness ratio. The member carrying compressive loads resulting from dead load and imposed load. If a member carrying compressive load resulted from dead load plus live load, then the value of restricted here is 180, the lambda. So in the similar way, a tension member, okay, in which if you observe a reversal of stresses, direct stress occur due to the loads other than wind and extreme forces, the value here is 180. So in the similar way, next point is the member subject to compression force resulting from only from the combination wind and earthquake actions. So then the value is 250. Okay. Then the compression of the flange beam against torsion buckling value is 300. Okay. In the similar way, so members normally acting as tie member in a roof stress bracing system not considered effective when it's subject to reversal of stresses into compression. The value is 350. So members always set to tension. Okay, other than pre-tension force, the value is of lambda slender. Okay, for your gate and other examinations also. So we'll see one review question on this. This was the gate question. A steel member M, capital M, has reversal of stress. Okay, due to live loads. Whereas another member N. Okay, here we have two members here. We need to compare the two members lambda here. So member M is reversal of stresses due to live loads, whereas another member N has reversal of stress due to wind load. So as per AS 800, what is the maximum tendency ratio permitted AS? So here they are given four options here. First option here is less for member M than that of member N. Second one, more than member M than for member N. Same for both the member, not specified in the code. Actually, they are specified in the code. We will see the technical term here for a member M. So we are getting reversal of stress due to live load. We'll see the table in the last slide. Okay, member subject to reversal of stresses due to what? Tension reversal of stresses due to other than wind and earthquake forces, the value is 180. So other than wind and earthquake force means, so it may be for live load or imposed load, the value is 180. That is for M, value is 180. If you go for N due to wind load, okay. If you go for N, so here you see it is resulting from wind and earthquake forces. Here the reversal of stress. Okay, this value is 350. That is for N member value is restricted lambda is 350, whereas for M the value is restricted 80. That is the value given in the code is for M is less value than N. So we'll see the option now. So first option here is less than M. Okay, less for member M than member N. This is what your correct option. Option A. So where for reversal of stresses if you get from other than wind and earthquake, the value is what? M. So with wind and earthquake, wind load, and that is N. Here for M, the restricted value is 180, whereas for N, the restricted value is 350. Therefore, option A is correct. So then move on to the design aspects of compression members. So normally they will, they will going to ask one mark question from this. Okay, we'll see that things. Normally the flexure members will be failed by flexure buckling. So actually we would classify the entire compression members. So what we're going to use in the steel structures into four categories, four buckling classes based on its limited width and thickness ratios. Okay, the classes are A, B, C, R, D. It is given in table number 7 of AS 800. So we have one formula in the code book. The design compressive stress. If you know the stress, we can calculate the area, load carrying capacity. If you multiply the area, design compressive. This the formula is given in class 7.1.2.1. Okay. So there is FCD equal to Fi by gamma m naught divided by 5 plus 5 square minus lambda square 0.5 or equal to say factor Fi gamma m naught, or that value must be less than Fi gamma m naught. So this formula you won't use. So if you remember this, it is a good. So for that they will use some of the values directly in the problem. Okay. So I told that we're going to classify the entire compression members in different classes here. So if you go for rolled steel I sections, so before calculating the strength of the compression member, we should check, or we should categorize the compression member into different classes. Maybe a class A, class B, class C, or class D. Okay. if you go for I section, so based on H by BF ratio and thickness of the flange, okay, here H by BF and thickness of the flange, we can choose the buckling axis after calculating the value about ZZ or YY axis. So we may categorize into A, B or BC categories. Okay, here if you observe here, so H by BF is for roller stitch section. The limits here is it should be greater than 1.2. Thickness of the flange must be less than 40 millimeter. The same way, thickness of the flange is greater than 40 and less than 100 millimeter. So we can categorize the classes here. So similarly for hollow sections, okay, for art rolled sections, you should remember these values at least. For art rolled section, the buckling class will be A. For core former section, buckling class will be B. Similarly for built up member, for channel section, T sections, okay, for circular sections having full area, full volume. So whereas hollow section is different, so full, the intersection circular area is different. For this, we can provide the buckling class as buckling class C for any axis. It may be a ZZ axis or YY axis. On any axis, we can categorize those members as under buckling class C. So correspondingly, we should take the stress coming under buckling class C from the code book to calculate the strength of the compression member. So from this table, what you can remember here is, so this thing. So you can remember for buckling, the built-up member and channel section T sections or angle sections. Okay, the buckling class is C. Okay, so next one of the important parameter in compression members are the effective length parameters. So they will give the effective length parameters according to the code. So based on for any column, there will be two ends. So based on end restraints to the given to the column or boundary conditions given, based on the restrainment, we can categorize or we can calculate the effective length of the column here. Okay. So first, if you go for at one end, for example, if you go for this problem, so first case, at the one end, the translation is horizontal movement. Rotation means what your rotation, what we're going to get at the end of the member. So at the other end, the same thing you have given here, translation, rotation. So based on whether you provided restriction to the translation or provided free access for translation of any joint. So based on that, we can categorize different categories here. Okay, we will see what are those categories. At one end, okay, translation. For example, if we take this case, so at one end we are given fixed condition. So if you this is what your fixed support, this is what your fixed support. If you provided fixed support, okay, if you provide fixed support, normally or always what the translation will be 0, rotation will be 0. Nothing but there will be restriction for the moment of translation and there will be restriction for the moment of rotation. That means it will give full restraint to the connection part. Therefore, when you provide fixed end, you can directly say, so it is given restriction for the translation and restriction for rotation. So at one end is restricted for translation. There is no horizontal movement for given to this member connected to the fixed support. So and also rotation restraint. So at the other end, so other end means this top end here. So top end is free. This end is not connected to any member or any support. Okay. Therefore, here the translation is free. So that means it can move in towards positive x direction or negative x direction. In any direction it may move in translation. Rotation means it can rotate. It may be clockwise rotation or anti-clockwise rotation. Since there is no restriction for here, so this free here, so it will go to rotate. Therefore, that's why this for this column is the cantilever. That is one side is fixed, other side is free. So based on the restriction at one end fixed end, other end is free. For this, they given in the code book, the effective length will be equal to 2.0 times of L, where L is the actual length. So this is what your actual length L. If you want effective length according to the IS 892.7, the value is 2.0. You should multiply with L. Well, this is also the same condition. So second problem, a given here, the translation is free at one end. Okay. So at other end, the rotation is restricted. In a similar way, all these conditions you should know. Why? Because they are asking frequently 1 mark question on this table. Okay, here if you observe third one, so if you go for next, so you should remember this table. So if you go for then the last one, the translation is restricted, and also and also the rotation also restricted at both ends. Since that is then, so therefore we should take corresponding values. Here if you see k value, what is k value? 0.65 times of L, where L is the actual length, whereas you should take this portion only. This is what your the effective length according to the code when you provided. Both are fixed ends, nothing but the other conditions, that is translation and rotation. Based on restriction condition, we can categorize this fixed suppose a member or a member to what at the both end. If it's fixed, you can provide 0.65 times of L. Okay, we will see 1 or 2 questions, review question on this. So in this one of the gate question, okay, the effective length of a circular electric pole of length L and constant diameter erected on ground is. So we'll read the question again. The effective length we should calculate now. Circular electric pole. This is a circular electric pole which is erected on the ground surface, having an actual length of L, capital L, and constant diameter. That is there is no tapering in the diameter of the bar. The diameter is constant from top to bottom. So say the same diameter they have maintained till from ground to top. For this we should calculate. So according to the series structures. So what is the effective length? So if you observe, if you represent this figure in the form of a support conditions here. So electric pole erected on the ground means if you provide any member to the ground, we're going to provide the fixity. What about other end? Other end is free. We are not provided anything on the other end. So therefore, the first one end is restricted against rotation and translation, whereas other end is not restricted. It is free for translation and rotation. Therefore, it will come under cantilever case. So therefore, our answer is 2.00 L. Option D is correct answer. So that is if you go to the table in the code book, this is what your first case what they given here. So ground here, on the ground they have erected a electrical pole here. Okay, this is what free end. Okay, this is what fixed end. So one end is what restricted, given fixity to the end which is inside the ground level, inside the earth. Other end is free. Here the allowing rotation and also translation. Therefore, your answer is 2.08. So this is what the question they asked in the gate exam. So go to another one question. Recently asked this question. Steel column is restricted against both translation and rotation at one end. So that is, so how we can represent it through the figure. A steel column restricted against both translation and rotation at one end means one end is fixed. Assume that I am writing the bottom end is fixed. And other and is restrained only against rotation but free in translation at the other end. That is, restriction only given to the rotation. That is, here they will going to give the roller support like this. Okay, that is the representation here. So it is giving restricted the rotation, but it will going to translate towards right or left side. Okay, then the theoretical and IS design values, nothing but according to the code, the effective length factor we should calculate here, or we should mark the effective length factor. Okay, theoretically we will provide what 1.0. When we will going to provide 1.0, you might have studied in strength of materials. If one end is fixed, okay, other end is roller or simple roller support, then we can provide the distance between the contra flexure. If you write the bending moment diagram, we're going to get like this. So here bending moment will be maximum at bottom end, other end is 0. This was distance between the bending moment contra flexure point, that is equal to 1.0. Okay, that length, that is what the effective length in case of theoretical values. If you go to IS 800, where we need to look into this condition, roller and fixed condition. If you go to the table here, so this is what your condition. So this condition they are given here. One end is restricted on for both translation and rotation. Other end is free for or translation, the moment is restricted here. Therefore, that is rotation is restricted. Therefore, your value is 1.28. So if you see the options here in the given question, so theoretical value will be the distance between the two contraflexure point in the bending moment diagram. The value is 1. So if you go for design values according to the code, what we seen in the last slide, the design value is 1.2. Therefore, option A is correct for this problem. Okay. So this was the two questions I have referred with respect to the effective length of the compression member. Move on to the angle struts. So for angle strut, this is the formula. If they ask, you should remember this. The member which is carrying what the compression in the roof stress, for those member we call it as angle struts. So when the angle strut, if you provided only single angle section, okay, on the single angle section, then the equivalent stress, equivalent slenderness ratio should calculate by using this formula according to the code. So when the double angle stress you're using, equivalent stress you can calculate, or the lambda we can calculate. Okay, so like similar to your compression member design of other members, where you should take here the effective length. What is lambda? Lambda equal to the effective length KL by R minimum. Where what is R minimum? R minimum is the square root of the moment of inertia with corresponding area. So if you want R minimum in x direction, then you should take Ixx by total area. If you want moment of radius of gyration about y axis, then you should take the moment of inertia about y axis to the area. And if you want R minimum, whichever is the least I value, that is moment of inertia, corresponding area you should take. So to know the strength of the compression member or the compression angle struts, this is what the formula lambda you should know. So in case of a single angle, you should calculate lambda E. That depends again on K1, K2, K3 factors, which is given in class number 5.1.2 of IS 800. Similarly, if you want double angle section, this is what the formula. What is that? Lambda equal to KL by R minimum. For angle struts, the buckling class is C. From table number 9C of IS 800, for given lambda, calculated lambda, okay, we're going to take the value of FCD from the steel code book. Then finally we can calculate the strength of the member. To calculate that, okay, here this is the formula KL into R minimum. For the thing here is what I am highlighting here is the KL, effective length for angle strut, the KL is the value. Where this K value according to the code, how much you should choose here is the effective length for a double angle strut is 0.7 to 0.85. K value. Okay, you should remember this value for angle strut. So similarly, you can in a similar way you can calculate a lambda KL by R minimum, which is similar to the exact other compression members for I section, other section. How you going to calculate the lambda and compression? In the similar way, you can calculate for double angle strut, whereas single angle strut is different. That is lambda we should calculate. Okay, then so this is what the point you should remember from double angle strut. The effective length should be 0.70 to 0.85. So I'll move on to next slide now. So some of the basic aspects of the laced column, that is built up column, which are they are all very important. They're given clearly in the code book in class 7.6 of ISAT. You should remember this. Here the effective slenderness ratio for what the lacing column you should take 1.05 times. That is 5% extra you should take as set of KL by R naught, the actual slenderness ratio. Whatever the actual slenderness ratio we have calculated for the laced column for a regular column. If you want to design as a laced column, then you should add 5% extra to account for shear deformation effects. So this is what affects slenderness ratio with respect to the laced columns, nothing but built up columns. So in built up we have two category actually in the syllabus, laced column and pattern column. When you're designing laced column, so we should take the effect slenderness ratio 5% extra with that of regular column to take care about the shear deformation effects. Okay. Then the width of a lacing bar. So how much is the width we need to choose according to the code. The width of the lacing bar must be the 3 times of the nominal diameter of the end bolts or rivet. So whatever the bolts here are used here, so that is the minimum is what, how much? 3 times of the nominal diameter. Assume that if you're using 20 mm diameter, minimum you should provide 3 times of 20, 60 millimeter, the width of the lacing plate you should provide it. So that is what the code says, the width of the lacing bar. These were some of the specifications about the laced column. So FH tenderness ratio is 5% extra, 1.0 times of the actual column. So width of the lacing bar is 3 times of the nominal diameter of the end rivet. The thickness here is here in the code, given in the code book, that must be greater than or must not be less than 1/14th times of effective length of the single lacing. Okay, for double lacing 1/16th time. Okay, so in the thickness of the lacing bar is 1/14th for single lacing, 1/16th of effective length for simple lacing. So assume that effective length is 7 meter, then you should take 1/14th of 7 meter. That is whatever the value you got, that is what the thickness of the lacing bar what you supposed to choose here. So in this slide, we have discussed with respect to laced columns, the effective slenderness ratio according to the code 1.0 times of actual value. So the width of the lacing bar 3 times of the diameter of the bolt. Thickness of the laced bar. Okay. For single lacing system, single lacing means we're going to provide only one side like this. Only one side. So that is we call it single lacing. If you provide this double lacing here on both the sides, okay, alternative lacing bars, then it will come under double lacing system. Here you see this is an example for double laced column. So where you should take the thickness as 1/14th and 1/16 for double lacing system. Okay, then so in some of the other information, so where the next important information is what is the angle of inclination what we can give for lacing bars. Okay, here what is the angle of inclination we can provide? The value must be not less than 40 degree, and at the same time it should not be greater than 70 degree. So that is whatever the value you chosen for the lacing bar, inclination, the value must be between 40 to 70 degree. So this is what another important information with respect to laced columns. So next is what is the force I can design the lacing elements. The total is just to transfer the total transverse shear Vt. That value is equal to minimum of 2.5% of the axial force acted in the member. Okay, that is if you take any column, if the load is acting 1000 kilonewton, so for how much load I should design the lacing the element. That value must be okay minimum of 2.5% of the 1000 kilonewton. Okay, whatever the axial load that is carried by the the column, it should design minimum 2.5% to that. So that is what the design value for lacing system. Then if you go for slenderness ratio of the column, what is the maximum slenderness ratio we can restrict it to with respect to design of lacing bar? Here is the value is 145 according to the code. Okay, from last two slides, okay, we have seen what some of the aspects of design of laced column, where we have discussed the effective slenderness ratio, the width of lacing bar, thickness of lacing bar, angle of inclination, the load carried by the lacing bar, and also the slenderness ratio, maximum slenderness ratio for lacing bars is it should not exceed 145, it should be less than 145. So we'll see one of the review question on this, the lacing bars. Here, in the design of lacing system for a built-up steel column, the maximum allowable slenderness ratio according to the code here is 145. You see in the last slide, the maximum allowable slenderness ratio is given in the code book here is 145 for laser system. We go for one more question here. So the square root of ratio of moment of inertia of a cross section to its cross sectional area is called the radius of gyration. That is R equal to square root of I by A. That is what your radius of gyration. Okay, moment of inertia, denominator is the cross sectional area. Okay, section modulus is different. Slenderness ratio KL by R. KL by R is slenderness ratio. Okay, radius of gyration is square root of R by I by A. That is what your answer. Option D is correct. Whereas section modulus is Z I by Y. If it is elastic section modulus, ZP is different. Plastic section modulus is different. Second moment area is what your I value, moment of inertia. So out of these four options, this is the correct answer. Radius of gyration, square root of I by area. So if you want R minimum, you should take I minimum. If you want any axis, the R value, you take corresponding the I value of that axis. That is your radius of gyration. So then see one more review question on compression member. You see the question here. A steel strut in a truss composed of two unequal, equal angles, 150, 150 into 10 millimeter thickness, connected back to back on the same side. Okay, on the same side of a cassette plate. The cross-section area of the angle is given. So sometimes we don't know what is the cross-section area. Actually, in the in actual studies that in B or BTech, we're going to refer steel tables for taking the area of the angle sections. So if they're given in the examination, definitely they're going to provide the area information. And also moment of inertia is also given here is 6335000 millimeter cube, Ixx equal to Iyy. The distance of the centroid of the angle from the outside surface Cx and Cy also given. That is, this distance is given here. Okay, that is 40.8. Then we should calculate what is the minimum radius of gyration. So here minimum radius of gyration is about y axis. So there this option 93, 46, 82, and 28, 29. So this is the figure we are written here. So first we should write the gusset plate on one side. So then you connect the angle section on the same side of the gusset plate. You should connect like this. If it is on the back to back, then how we should connect? So we should write like this. This is what is back to back condition. Okay, if you write like this, but we are since they have given as the same side, we have provided both angles on the same side here. Then I want what they are asking here is radius of gyration. So we know the formula for radius of gyration. I by square, square root of I by A, where I is the moment of inertia. So here, since we calculate for two cross-sectional area, you multiply the area with 2, you're going to get the total area. Okay. Here Iyy, so Iyy for one angle is given is 3633500. For double angle it should be double. So therefore R minimum equal to what? Iyy by 2a. Okay, Iy here is the 2 times of that is 1267000 divided by 5842, 46 millimeter is your answer. That is, here the weakest axis is the y axis. While calculating that, we should consider both the angles. That is, one angle and another angle, top and bottom angle with respect to this x axis. Okay, we should calculate both. Therefore, while calculating the area, I have taken 2 times of the area, and while calculating the Iy of the material, I have taken 2 times. So then we went for the calculation of R minimum. Iy by total area, that is 2 times of the single angle. It is 46. For example, for the same problem, if they ask maximum radius of gyration, then you should calculate about xx. You calculate a xx value and also area value. So you will going to get what your maximum radius of gyration. So that is the thing here. So next, if you move on to some of the design aspects of beams. So beams or structural members will go into, it is having less cross-sectional area compared to its longitudinal direction. Okay. In beams, we might have studied the two types: laterally supported beam, laterally unsupported beam. Where laterally supported beam means the beams which is what deflection is vertically, exactly vertically. There is no horizontal deflection. So that we can achieve when we provided the lateral restrainment to the beams. Those beams we call it as the laterally supported beam. So how we can provide that? By providing what? The compression, by inserting the compression flange inside the slab. Okay. So if you give the restriction to the movement of this compression flange towards in horizontal direction, then those beam we call it as laterally supported beams. Okay. Okay, when you move on to the design strength of the beam, so it is governed by lateral torsion buckling. When not adequately supported, that will it will fail by lateral torsional buckling strength. We should check, and it will fail by lateral torsional buckling. So when the laterally supported beam is given, so that is when the compression flange is properly inserted, there is not allowing any torsion, then therefore that will come under what lateral supported beam. If they are not provided the sufficient adequacy with respect to support against lateral buckling, so then it will govern by lateral torsional buckling strength. Okay, that will come under laterally unsupported beam. So we'll see one. So next, one of the question in GATE, that generally based on deflection criteria of the beam, they asked this question. That generally the maximum deflection to span ratio of a steel member should not exceed here is, so 1/355 is the answer. So you should remember this. This is what the based on the deflection criteria of the beam. So what is the maximum span to depth ratio? Deflection to span ratio here is 1/325. It should satisfy. Otherwise, it will the finishing what you given in the structures, it will be appeared with cracks. Therefore, we should maintain this deflection to span ratio equal to 1/325. So then, if you move on to the next question here, in ISMB 500, that is Indian Standard Medium Beam, having a depth of 500, is used as a beam in a multi-story construction from the viewpoint of structural design. It can be considered to be laterally restrained. When it is going to call laterally restrained, the beam. So actually we have discussed two conditions, laterally supported and laterally unsupported conditions. So when you're going to tell us the laterally restrained condition or laterally supported condition. Option A here is the tension flange is laterally restrained. For example, to take a beam like this, okay, if you take the cross section of the beam, assume that the cross section here is I section. This is what your compression flange. Top flange will be subject to compression. After application of the force, the beam will go into bend like this. The beam will go into bend like this after the application of the force. Okay, it will go into bend like this. The bottom will be under tension. Therefore, this bottom flange we call it as tension flange if it is I section. So according to the options, what they are telling is tension flange is laterally restrained. Second one, compression flange is laterally restrained. Third one, web is adequately stiffened. So fourth option is conditions A and C are met. So actual answer here is if you provide the compression flange restrainment, lateral restrainment to the compression flange. So this will be your answer. So that condition we call it as lateral restraint condition, other than tension flange and stiffness. So if you're not provided, lateral restrainment to tension flange, if you're not provided sufficient adequate stiffness to the web also, if you provide sufficient restrainment to the compression flange, that condition we call it as laterally supported conditions or laterally supported beam. Okay, so in the beam design, I'm continuing the thing. So in the beam design, so when that factor design force, this was the force what we're going to get from the external load, factor design force does not exceed 0.60% of VD or 0.6 times of VD or 60% of VD. That is, VD is nothing but design shear strength. Then that we call it as, that condition we call it as low shear case. What do you mean by low shear case? Low shear case is nothing but what? When so low shear case is nothing but when your design shear force is less than 60% of VD, then we call it as low shear case. So when the design shear force is greater than 60% of design shear strength of the member, then that will come under I shear case. You should remember that value. So then if you go for this with respect to shear, if you go for bending moment strength, this is what the formula. MD or the design moment equal to design bending strength equal to beta ZP Fy by gamma m naught, whereas beta is the ratio of ZP to ZE for semi-compact and compact section, whereas beta is 1 equal to 1 for plastic section. ZP is plastic moment, Fy is the yield stress of the beam, the material, gamma naught a positive factor. Okay, and this value must be less than 1.2 times of ZEFY for simply supported beam, 1.5 times of ZEFY for cantilever beams. So this is what with respect to your moment strength for laterally supported beams having low shear case condition. How to decide low shear case or high shear case? First, you should calculate design shear force acting on the beam. Okay, design unbalanced shear force. So the value must be less than 60% of VD. Then it will come under low shear case. Then if you come under low shear case, here we have the formula to calculate design bending strength. This is what the formula. Here this value must be less than 1.2 times of ZD Fy gamma m naught, where ZD is what elastic section modulus for simple supported beam. Here for cantilever beam, the value must be 1.5 times of ZD Fy gamma m naught for cantilever beams. This is what the bending moment strength calculation. Okay, if you move on to the in the same thing, the fracture design strength, that is VD. I have told here to categorize the low shear or high shear case, we should calculate VD. So how to calculate VD? So VD equal to area of the portion in the beam resisting shear into the FY of the material divided by root 3 gamma MW. What is the in case of I section? Web portion will going to take care about shear, whereas flange portion, these two flange portion will going to take care of bending moment. So therefore, for I, if it is your beam is I section, your area will be T into H. So H is the height of the web and TW is the thickness of the web. So that is what equal to area of the web into corresponding yield stress of the material root 3 by gamma. This is what your the factor design strength of the shear strength of the beam. Okay. So in this slide we discussed three conditions: low shear case and high shear case, and the design bending strength of the beam and design shear strength of the beam. Next, some other checks we need to do for beams are web buckling and web crippling. So in this figure we know that web crippling, this the concentration load are that the supports. Okay, when the points are acting on the member, what you're going to get, the web portion of the beam may buckle locally, may failure locally. That condition we call as web crippling. So web portion is in the buckle, the entire web is buckle, so due to the application of concentrate load acting on the beam or at the support. Okay, at the end of support, if you have beam like this, I section, if you have end support, here you're going to get the maximum shear from the support reaction. So therefore, this portion is very, very critical for web buckling and web crippling. So we should check both of checks, web coupling and web buckling here. So therefore, this is what your buckling and crippling cases. For that, we have general formula in the code book, but the thing you need to remember here is for the web buckling case, the dispersion angle must 45 degree will going to take in case of web buckling. In case of web crippling, we should take 1.1 is to 2.5% times of the dispersion. That is, if you have a beam like this, if you have the support, then for web crippling, we should take 45 degree dispersion. Okay, for web buckling, we should take 1.25, 1 is to 2.5 times of dispersion with respect to the bearing length of the support, we should consider. Okay, you will see one of the problem here on the high shear and low shear cases. Assuming there is no possibility of shear buckling of the web, okay, the maximum reduction permitted in the IS 800-2007 for low shear case, designing bending strength for semi-compact section areas. Semi-compact of section due to high shear is option A 0. Okay, option B governed by the area of the flange, option C 50%, option D 25%. For that, what we need to do here is for semi-compact section, we should calculate MD. So semi-compact section, ZP will not come into picture. Therefore, so in case of low shear case, VD is less than or equal to 0.6 VD, MD is here. MD equal to ZD FI gamma m. In case of high shear also, MD is ZD FI by gamma m. Therefore, if you compare both the MDs for semi-compact section, the values are same. Therefore, so there is no question of giving reduction to the shear. So therefore, here the option here is option E. So whereas if it is the plastic section, then in MD you should check with ZP also. Instead of ZD you should calculate for ZP. Then you should compare with the elastic section modulus. Therefore here is the answer is, so there is no reduction is needed in case of, if you can take low shear or high shear case, in both the cases we are getting what the same values. Therefore a reduction is 0 here. That is what your option. So then this was one of the question they asked on web bearing. Okay. Web crippling condition here. So we'll see the problem now. A rolled I section beam supported 70 mm wide bearing plate. So here B equal to 75 mm. What is the web bearing length? So this is what the bearing length given 75 mm. Okay. As shown in figure, the thickness of the flange and the web of the I section are thickness of the flange. So this thickness of the flange here is, or here, thickness of the flange here is given as 20 milliliter, Web thickness they given 8 millimeter respectively. The root radius of the I section is 10 millimeter. Okay, root radius nothing but if it is I section, okay, here. So thickness of the flange is given is 20 millimeter, thickness of the web 10 millimeter. Here the root radius is this one. The curvature of the the flange to the web portion where given the curvature, that curvature we call it as a root radius. That is 10 millimeter is given here. The material stress is 250 MPa. Partiality factor for yielding area is 1.10. So now what we need to calculate here is, as per the IS 18-2007, web bearing strength in kilonewton rounded up 2 decimal places of the beam here. So for that we have the formula in the code book. So I told that in the last slide, the web bearing strength here or web crippling, here you should go for 1:2.5 dispersion. So same concept I should use here to calculate the length, effective length here. That is, this is the bearing length, B is given. Plus, we should take what this dispersion here, N1 equal to, what is the dispersion equal to N1? This was the dispersion, that is equal to 2.5 times of thickness of the flange plus root radius. Should remember this value. So then if you go for web bearing strength, so web bearing strength is what? The area of the web under the concentrated load into corresponding stress. So load carrying capacity equal to area into stress. So area here is Fi by gamma m naught, where strain area, area here is stress is here is Fi by gamma m naught, where area here is B plus 2.5 into thickness of flange plus R into TW. Here all the information is given in the problem. So B is given as 75 millimeter, TF given as 20 millimeter, R is given as root radius here 10 millimeter is given, thickness of the web also given 8 millimeter. So Fi yields of the material is given 250 MPa, gamma m naught is also given. So you substitute to the formula and calculate the value, you're going to get 272.73 kilonewton is the web bearing or web crippling strength of the beam. So here what you need to remember here is, so in case of web crippling, so N1 becomes what? N1 becomes 2 times of thickness of R, where here what is N1? This portion is N1. Okay, this portion is N1. So the length, bearing length, effective bearing length you should take here is Bn plus B plus N1 into the thickness of the web. So this N1 will vary for web buckling strength. In case of web buckling, you should need to take 45-degree dispersion. Whereas in case of web crippling or web bearing, we should take 2.5 times of that. That is 2.5 into what? Thickness of flange plus R. So you should remember these basic formulas. Finally the basic formula here is, if you want the load capacity or strength, you take the area of the member, area, you take corresponding stress. That is what the formula here we getting 272 Newton. This is the one question they asked on web bearing strength. Okay, now we'll move on to one of the important topic, plastic analysis. Okay, plastic analysis. So this where you make it in researchers, if you read the connections part, plastic analysis part, it's more than sufficient. Definitely you're going to get one question either from plastic analysis or from connections, from that is bolted or welded connection. So we'll see some of the technical terms which are involved in the plastic analysis. Plastic hinge. So plastic hinge is the zone of yielding due to flexure of the member. So when the member subject to excessive load, that is steel member, all the fibers will yield in the material. Finally, they're going to form a hinge. After the formation of the hinge also, so the beam will going to take the load, the member will going to take the load by continuous rotation. That portion we call it as plastic hinge. Next is plastic moment. So the moment at the time of the plastic hinge formation we call it as plastic moment, that is MP. So plastic section modulus, where you have seen till now the elastic section modulus, where ZD equal to what? I by Y is the elastic section modulus. Whereas plastic section modulus we should calculate according to the code or the here. So plastic section modulus that divides the area into two equal parts, that is A by 2 into corresponding central distances we should take for all the elements. That is what your ZPZ, elastic section modulus. Shape factor is the ratio of moment capacity, plastic moment capacity to the elastic moment capacity, nothing but. So plastic moment, the answer is ZP. And if you go for the section modulus, so elastic is ZE. So what is the shape factor? It is the ratio of plastic section modulus to elastic section modulus, or plastic moment to the elastic moment. So next question is, what is equal area axis? This is the new word we are seeing here. This will be there only in plastic analysis. The area which the section, the axis in which the section will go, that axis will be going to divide the area into two equal parts. That axis we characterize equal area axis. Okay, the mechanism. So after the application of the load, the plastic will go into form. The indeterminate structure will convert to determinate structure. So okay, that condition we call it as mechanism condition. So next is, to perform plastic analysis, what we need here is number of plastic inches required to convert any regular structure or indeterminate structure to a mechanism. So how many plastic inches are required here? So R plus 1. So capital N equal to R plus 1, where R is the degree of static indeterminacy plus 1. So number of plastic possible independent mechanisms equal to small n, that is equal to n capital N minus R, where capital N is R plus 1 minus degree of static indeterminacy. This is what the possible locations of mechanisms. So I think where are you going to get the plastic inches? So in case of fixed supports, we're going to get the plastic inch. So that is here. So after the application of the load, so we're going to get the plastic inch. So then if both our ends are fixed the ends, so that is the first condition. We're going to get at the both the ends. Then under the loads, so if you have a loads, under the loads, you're going to get the plastic inch. Okay, under the change of property of the material, assume that we have what different material here, value is I, here we have I by 2, the moment of finish is changing here. So at cross sectional element, you're going to have the plastic inch formation chance. And wherever if you changed the materials here, assume that till this portion if you use concrete, then if you go for any other material, steel and other material, then at this junction we're going to get a formation of plastic inch. So these are the possible locations of what the plastic inch formation. So at fixed supports, okay, where to form a plastic inch, you should take what you should the moment should be MP, and there will be a rotation, and also there will be contribution of MP moment. So it will be possible under fixed support, at fixed support, under point load, okay, at change of cross section of geometric properties of the materials, and change of cross section, change of material properties at the junction where you are going to receive our plastic. What is that? The plastic. So before going for problems, we'll see the cross sectional properties here. So we can categorize our steel structures into 4 categories: class 1, class 2, class 3, and class 4. So class 1 is what the plastic section. If you observe this figure, so all the fibers, this is what the y-axis it gives the moment capacity, where x-axis you will get the rotation capacity. I'm giving more rotation here. Then that come under class 1, nothing but this cross section at this stage, if we are able to develop the plastic inch, and this section will have the rotation capacity required to failure of the structure by the formation of plastic mechanism. So that we call it as class 1 material, nothing but plastic. So then class 2, all the fibers will at maximum yield stress Fy, okay, but it is inadequate to develop the plastic inch, plastic rotation capacity. Therefore class 2 compact section. So semi-compact is here is class 3, where extreme fibers yielded a maximum stress. Okay, whereas fourth one is slender. So because of here the Fy, or the yield strength of the cross-sectional material, that is the extreme fiber, is less than Fy. Here the yield stress is Fy. Here also all the fibers yielded Fy. Here also all the fibers yielded Fy. Here only last extreme fibers yielded Fy in case of class 3. Whereas in class 4, before the application of the load, the member will go to fail by buckling. And in other words, what you can say, the yield strength in the member is always less than Fy. Therefore, those members you can as class 4 members, as slender members. So normally, according to the code, we will classify into these 4 categories. You should remember these 4 categories. So next is what limiting width to thickness ratio. Okay. So how to classify the cross sections? So here I have told that plastic, compact, and semi-compact. Actually, code is allowing only 3 types of sections to use for practical purposes. They are not allowing to use slender sections. Okay, where those sections are very slender and they will fail to its own weight, because of its own weight, because of local buckling, it will fail. Therefore, we suppose to use only plastic, compact and semi-compact section. This is what the width to thickness ratio that is provided in the table number 2. This is one of the main criteria to we need to observe to classify the cross sections. So next is I'll see one review question on this classification. So this is one of the gate question. As per IS 800-2007, the cross section in which the extreme fiber can reach the yield stress but cannot develop the plastic moment of resistance due to local buckling. So this we call it a semi-compact section. So this because of local buckling, it will not provide only the if you observe here, only extreme fiber reaches stresses. So if you observe in the original figure, this condition we are telling class 3 condition, only extreme fiber reaches Fy, but inadequate to produce the plastic in the plastic rotation capacity. Therefore, that will come under class 3 as semi-compact. Whereas compact, all the fiber reaches Fy, so inadequate plastic capacity. Whereas plastic section or class 1, all the fibers yielded Fy and possible to produce a plastic inch and plastic moment capacity. That is what your class 1 section. Okay, here for this question, answer is semi-compact section. So next here is some of the review questions taken here. 1 mark question. In the theory of plastic bending of beams, the ratio of plastic moment to the yield moment, that is MP by ME, you call it as what? The shape factor. We discussed in the last slide, shape factor. So here I have shown the sum of the shape factor for different cross sections. For rectangle 1.5, for I section 1.14, for diamond section 2, that is what your shape factors. Whereas shape factor is what? MP by ME or ZP by ZE. So plastic section modulus to elastic section modulus. So diamond is 2, triangle is 2.34, circle is 1.7. So amongst it, we see having highest. So highest is having a triangle. Triangle is having highest shape factor. So therefore, if you want to give the section to any of researchers, if you provide triangle shape, that will take more moment and load. So the another review question I have taken here. The shape of the cross section, which has the following largest shape factor here is rectangle is 1.5 is in the table here, diamond is 2, I section is 1.14, solid circular is 1.7. Therefore, answer is diamond. The value is 2. This is highest shape factor among these 4. But whereas if you take the basic cross sections, so triangle is having highest shape factor. So if the member is having highest shape factor, the member will be it will take more load and more moment in actual structure. So that shape we need to practice in this design. So then if you go for what the next question, if YY is the central axis of the T section subject to plastic moment. So this was the central axis subject to plastic moment, neutral axis of the T section, where top one is Z axis, bottom is X axis. So what they are asking here, then the neutral axis lies between. That is, when your section is set to plastic moment state. So where is your neutral axis? So actually, so when the section plastic state, neutral axis will be our equal area axis. So normally that will be there towards that area or equal area axis will divide the total area into 2 equal parts. At that stage, neutral axis becomes equal area axis. The axis will be lies between here, y by to z axis. Okay, here you're going to get equal area axis. So nothing but the equal area axis is nothing but neutral axis for your plastic material or plastic section material here. The answer here is above z line is wrong. So between y and z is correct. Option B is correct for your section. And when the stage of formation of plastic moment, the area we should take here is section area we should take here is z to y. Okay, next. So this was the another question. So shape factor for rectangle is, you should remember this value, that is 1.50. So now we're going to tell how to calculate this. Okay, so you take the rectangle shape. So width is B, depth is D. Okay, this was D by 2. So this what the area stress block diagram you have taken. So we know that shape factor is plastic section modulus to elastic section modulus. So nothing but ZP by ZD. So ZD we know that that is I by Y is the ZD. Where I is for this rectangle we know that BD cube by 12. Where D is the y max from the extreme fiber to the center, that is d by 2. This is what your d by 2. Okay, d by 2. Total area is bd square by 6 is zd. If you want to calculate zb, this is the new thing you are studying now. So zb means you should take this entire area into two equal parts. Two equal parts. Here I have number 1, number 2 element. I have divided the total into equal area. That is okay. A by 2, you can call it as. Multiply with y1 and y2. Y1, but that is, so we should mark a centered here from this equal area axis. This is what your y1. For bottom, this is what your y2. So a by 2 into y1 plus y2. So area equal to b d by 2 into y1 here is d by 4. What is where is the location of centered for this first element? So d by 2 by 2, that is d by 4. Correct? So from here, from the central axis, neutral axis or equal area axis, the answer here is d by 4, the y1 value. So zp equal to what? We should divide the total area into equal area, equal areas. Okay, by writing the equal area axis. Then you take individual area corresponding central distances. If you take individual areas here, what is the individual area here? So in total area by 2, that is b into d by 2. That is what they have taken here. You multiply with d by 4 and d by 4. Corresponding central distance d by 4 and d by 4. We are getting answer here is bd square by 4. Therefore, shape factor here is what? Top thing here is zp, that is bd square by 4. Bottom here is bd square by 6. 6 by 4 equal to 3 by 2, nothing but 1.5. This is what the way to calculate the shape factor, nothing but the zp. We are all known for z. So the I by way can calculate, in a short time. Whereas for zp, first we should mark the equal area axis. Then you take all the elements above the equal area axis, below the equal area axis, and what you do, you take corresponding areas and corresponding center distance from the equal area axis. That is what your zp. Then you take a ratio of zp to ze. You're going to get the shape factor. For rectangle shape, 1.5 is the shape factor. Okay. Then move on to the I section here. I section in a similar way. In the similar way, what they are asking here, the dimensions of the symmetrical welded I sections shown in figure. The flash section modulus in a along weaker section. Here weaker axis is y axis, we know that. So this what y axis, weaker axis here. So you take area by 2 and take the corresponding distances. Okay, both the neutral axis and this portion also, we are going to get the zp as 89.9 centimeter cube. It's for your answer. So please go through it. This is exactly similar to what your previous problem, rectangular problem. So I will move on to the important problems now. The plastic moment capacity of NEP. So you should remember some of the basics. The beam condition, the plastic moment capacity. Here I have taken proper cantilever beam. A proper cantilever beam is shown in figure. The plastic moment capacity of the beam is MP. The collapse load is. So we should calculating now from this. These are all very important problems. The collapse load. So here they given proper cantilever beam, where at one end we have that is a roller support or a vertical support. Other end we have fixed supports. So this would be acting exactly tail by 2 equal, half span. So now what is the answer? The plastic load, the collapse load here is 8 MP, 4 MP, and 6 MP and 12 MP. Answer is 6 MP by L. You should remember this. No need to calculate in the exam. But I will tell how to calculate this. So first we should see what are the possible locations of plastic hinge formation. So I told in the last slide, the plastic hinge formation will be at fixed support. That is here, 1 inch you will going to get. Okay. Next, under the load. Okay. Whereas here, this will not, at roller also it may, you will not receive any plastic, formation here. Why? Because this will not allow any moment. It will not resist any moment. Therefore, we will going to get plastic hinge only under the load and at support. Okay, and at that too, the fixed support. So where if I write the plastic hinge here at P point at support point, so MP I should write to keep the beam in equilibrium, I should write in anti-clockwise direction, opposite to the deflection. Actually, beam is deflection because of the load downward. To keep the beam in equilibrium, I should apply the moment in the upward direction. Okay, this is what your moment MP. You are applying MP here also MP, where theta is the rotation here. Okay. Principle of virtual work to calculate the collapse load. So that is external load equal to internal load. So what is external load? Because of this load P, you should calculate the force into delta, force into deflection. In a similar way, in this figure, we should calculate the virtual work, that is the moment and the corresponding rotations here. So if you take here, moment here is MP, corresponding rotation is theta. So I'm calculating what the virtual work here. Again, internal work done, I'm calculating here internal work done, MP into theta. Whereas if you go here, again MP into theta. So internal work here is 3 MP theta is the internal work done. If you go for external work done, that is P into delta. Where what is delta? Delta is the deflection under the load. So I want this delta. For that, to calculate this delta, okay, P is known as external load. I want this delta. To calculate that, I will take separate triangle like this. Okay, so this is my delta, this what theta. So what you want is tan theta. So I want delta, that's why I take tan theta. So delta divided by opposite side by adjust, that is L by 2. So since theta is very, very small here, so tan theta becomes theta. So theta becomes what? How much? Delta into L by 2. Where what I want is only delta equal to theta L by 2. So this is what your delta or the deflection under the load. Okay, therefore if you calculate the external work done, that is P into delta is L by 2. So for all the problems, delta we should calculate under the load only using the triangle, using this triangle. So if the L is what is the length of the span here is L by 2, then you're going to get L by 2. The corresponding theta you can take directly. Otherwise, you can calculate from the basics. Tan theta equal to. Okay. So now this is what your 1 second. This is what your internal external work done. This portion. This is what your internal work done. 3 MP theta equal to PL theta by 2. Therefore, if we equate these two by the principle of virtual work, okay, this P equal to 6 MP by L. So this is what your collapse load for propped cantilever P. Okay, so you should better you remember these values of propped cantilever and fixed beams. Okay, we'll go for next problem. So here they given provided like this one problem. The plastic modulus of section is ZP is 4.8. The shape factor is 1.2. Plastic moment capacity of section is 120. What is the yield strength in the material? So we know the formula here is ZP is given here, MP is also given, shape factor is given. We know shape factor equal to ZP by ZE, where ZE equal to what? How much? So shape factor is no 1.2 equal to ZP is 4.8, 10 power minus 4 divided by ZE. ZE equal to 4.10 power minus 4, where from that we can calculate the yield strength of the material, that is Fy in this problem. So next, if you move on to next problem, where in this problem they given fixed beam. For fixed beam, we should calculate the the ultimate load, collapse load. So for this one also you should remember for proper cantilever 6 MP by L, whereas for fixed beam 8 MP by L. I will tell how to calculate this. So fixed is parallel having a moment capacity of MP. The ultimate center constant load will have is 8 MP by L. How to calculate this? This method here they have applied the static load method, not a our virtual work method. Here they apply static moment theorem. So they have written a bending moment diagram here. So for actual thing, for actual load, WL by 4 external bending moment diagram, and due to fixity they have written MP. So finally they equated fixed moment, internal moment to the external moment. So finally they got 8 MP by L. Otherwise, for the same problem, what you can do here is you apply this last problem concept, proper diameter concept. There is a formation of 3 possible locations of plastic inch here. So you calculate delta, you apply MP, okay, to keep the body in equilibrium. So here in all the cases you will going to get MP. So you calculate internal work done 8 MP, MP theta plus MP theta plus MP theta plus MP theta. Then you calculate what your external load, external thing, that is external work done, that is P into delta is L by 2. So if you equate those two by principle of virtual work, finally you want to get 8 MP by L. So my thing is here you need to remember the value for this collapse load for both propped cantilever and also for fixed beam. Propped cantilever 6 MP by L and for the fixed beam 8 MP by L. If you go for one more problem here, okay, this was the second 2 marks problem here. The plastic collapse load for the WP for the proper cantilever supported 2-point load as shown in figure. This is what the problem. So this is not a 6 MP by L. So answer is different here. Answer here is 4 MP by L. So don't directly mark 6 MP by L. Why? Because so in the proper cantilever beam in the previous case where we have only one load, that two acting exactly at the center. Whereas here we have two loads. It's acting L by 3, L by 3, L by 3. Therefore, now we should go for principle of virtual work method. First, you calculate what you first to identify what are the possible locations of plastic hinge. So we know that it will raise at fixed end, and also we may get plastic hinge at a support. Therefore, here if you go for the basic method, degree of static intimacy you're getting as 1. Number of plastic hinge will be formed equal to R plus 1, that is 2 formation at a time. So here they have taken the first condition, first case of beam mechanism. So at A is 1 and also below the W also you're going to get 1. This is what MP theta, this was MP theta, again MP theta. This is what your internal work done. We are written here. The thing here is to calculate external work done. To calculate external work done, we should calculate delta here. We should calculate delta here. So where delta always you should calculate below the point 2. If you observe here, so here this span is L by 3 or L by 3 plus L by 3. Calculate for the alpha. For if you go for theta, delta will be L by 3. So therefore, you should express alpha in terms of theta. That is, for this delta, if you calculate by considering the left-hand side portion, then you're going to delta equal to L by 3 theta. If you consider right-hand side portion, you're going to get 2L by 3 alpha. If you equate that, since with delta equal to these two, if you equate that, you're going to get theta equal to 2 alpha. So while calculating the answer, anywhere if you come across theta, you can substitute equal to 2 alpha, theta equal to 2 alpha. Then calculate, equate internal work done equal to external work done. Okay, you will going to get the W as 5 MP by L. In the similar way, you go for second case. You go for second case where you will going to get another 1 inch and below the second point load. You calculate the internal work done and external work done. You're going to get 4 MP by L. So where your answer is 4 MP by L. The least value your collapse load is 4 MP by L. Okay. Now this what the problems we discussed till now. So this was the one of the problem where the delta is always you should measure under load, and when the spans are not different, when the loads are eccentric, you should take corresponding length carefully, and you should express alpha, the slopes in terms of other. That is answer here is 4 MP by L for this problem. So in the next thing, so this is what the negative work problem. So please go through it. Okay, this is what the negative work problem. Here the answer is 6 MP by L. So because of application of this load, there will be negative work done by the P2 by load. This load we need to deduct while calculating the the load collapse load. So please go through it. And here one more problem here we have. So here we have different cross section, 3 MP capacity here, MP capacity here. At this tension we're going to get one more plastic hinge, where in this problem you should calculate. See, this is also one of the previous year gate problem. Here whichever is least C value, that is your answer. If you take first case means here under the cross section of load you're going to get plastic hinge at supports. Then the C value is 6. In the similar, if you go for mechanism 2, you're getting 3.33, where you are getting plastic hinge under the point load and at supports. Both are fixed supports here. Okay, if you consider that condition, you're going to get CS 3.33 your answer. Okay, thank you. So please. So I thank each and everyone for patient listening. I thank our beloved HOD, Dr. S.K. Prasad, and organizer Dr. P.K. Umesha for giving me this opportunity to share some my thoughts on steel structures. Thank you all.
Thank you very much, Rajeeth sir. It was indeed an excellent explanation by you on steel structure, a continuation of second part. And with this, I thank Professor Rajeeth T J, and I request all the participants to fill the feedback form, which is posted in the YouTube comment box. Please give your valuable feedback. And also please join us at 3:45 p.m. In exactly after 15 minutes. We'll be having second session of today by Professor Sharmila A on wastewater treatment. So please join us at 3:45 p.m. Thank you one and all.